Hello everybody, and welcome to the GWS Game Corruptor tutorial. This is just designed to get everybody familiar with the basic functions of this new Game Corruptor that I have created. Let me expand this so you can see all the functions. First of all, what is this Game Corruptor, and what makes it unique from anything else that you've ever seen? As you've seen, there's two major ones out right now. You have the Vine Sauce Corruptor, and you have the RTC Real Time Corruptor, which works off of the BizHawk emulator. This is more similar to the Vine Sauce Corruptor, except for it does it differently. This one, as opposed to going through specific increments in order to reuse corruptions, this one actually goes through the assemblies, and it will search for the specific bytes in the search query, and it will corrupt based on a number of simple models. Some of these models are 4 bytes, some of these are 6 bytes, but that's a little bit of technical information. You guys are wanting to kind of know what the hell all this is. So we're going to get to that. First of all, select file, pretty self-explanatory. Aladdin, I haven't had too much success corrupting that. So we're going to go to my favorite game to corrupt, and that is Zelda. But we're not just going to go to the Zelda. And this is a little tip for everybody watching this. If you're going to corrupt Zelda, go to the VT randomizer. It's called the VT randomizer. Google search it, and as long as you have the Japanese version of Zelda, you can get that from various ROM websites. You upload that there, and it'll produce a ROM for you, and that produces unique advantages such as not having to start from Link's house, which can expand your ability to corrupt that game. But okay, so first of all, we've selected the file, and there's no indication here whether the right file's been selected. Perhaps that's something I can add. This is just my initial build that I am going to be releasing to whomever wants to download it. Because I have all this here, so I just figured I'd release something. Might as well. Okay, first of all, corruptions. Fairly self-explanatory again. This is just the number of times it will run a corruption based on any of these, and it's usually just 1 byte corruptions. So this has 200 here. You can expect about 200 different individual bytes to be corrupted, in which a byte, if you don't know, it's just a single value between 0 and 255 that basically can determine the value of anything from what graphic is displayed on the screen, such as a piece of Mario's like a piece of Mario's sprite, like a part of Mario's image on the screen, or like a bush graphic or the ground or any number of things. Or it can represent like the number of lives, how high Mario can jump, how fast he can run, and a lot of things you wouldn't even understand, because part of the cool thing with these corruptions is you get to know how intimate things are based on what the corruptions could stretch out. Like, for example, if you play Super Mario World, you hit a Yoshi block, Yoshi will have a little bouncing animation, and that animation has a value. So, for example, if you have if it corrupts the correct byte, what could happen is, say, like, Yoshi bounces up maybe like a quarter of an inch, Yoshi could bounce up and down half the screen. You have a hell of a time getting on him then, won't you? But, just things like that. So, okay, so what's this? This is based on this is basically going to be how some of the bytes are corrupted. Like anything that can be corrupted using any value will have these. So for example, you have this const load store. We'll go through what these are later. This works off of this Dropbox. Your compare branch works off of it. Anything goes works off of it. And quite a few of these reads and writes operates off of it, but a lot of these will not work with that, at least initially. We'll show you how you can change that as we go through here. Okay, so what are these individually? This is called const load store, and what this does is this will search for a loading routine, anything that loads an accumulator. I haven't included the other registers other than the accumulator. The accumulator is basically just a value that's stored on the processor that can be stored into any address, or any address can be read from it. So what this will normally do is, the way processors will work is it'll read from one address, or it'll read some kind of immediate value. So for example, you can have a pseudo instruction called load 5 and then store an address 30. That's what this will do. And the value that it stores will be based on this. And I guess this is a good time to go through what these mean. And we'll go through quickly. Random just picks any number between 0 and 255. Random signed will take the current sign of the number, positive or negative, and then it will pick a number between 1 and 127, 0 and 127, and it will store it there, and then it will randomize the sign of that byte. It's also known as a sign bit that it randomizes. 0 to 50, self-explanatory. It'll just pick a number between 0 and 50 to store in it. And then you have between 0 and 5. Same thing there. Negative 50 and 50, and negative 5 and 5. Same thing. Whatever byte can be randomized that way. Div2 divides the number by 2. Mul2 multiplies. Div4 mul4, div8 mul8, same thing, divides by 4 and multiplies by 4, divides and multiplies by 8 respectively. Invert sign turns negative numbers into positive, positive into negative. Mirror is interesting because it will it will take the byte and it will subtract it from 255. And so what you get is, say you have, Mario has 10 lives, so the number is 10. So you mirror that byte, and instead of 10 lives, Mario will have 245 lives. So quite interesting there. So it basically takes how extreme the byte is and mirrors it the opposite way. And of course, the closer things are to 128, the less extreme. These truncate bytes, these work at the bit level. It's a little bit difficult to explain, but you take a binary number, for example. Like, I'm pretty sure most of you would know what binary is. It's ones and zeros, basically. So you have something, for example, let's say you have a number that is in binary 11110111. If you truncate at byte 7, that becomes 10000000, because what it does is anything, because basically a byte is just 8 bits, right? So it will just take the first bit, it will retain that value, and then everything else is what's called truncated, which just is a fancy way of saying everything beyond this point is 0. So same thing here. So say you have that same number 11110111. This would just be 1 1 and then everything else 0. 1 1 0 0 0 0 0 0. And then the same thing here. This will retain the first 3 bytes, and then 4 and 5, etc. And these can actually produce, like, usually when games are difficult to corrupt, these are often your saving graces, because what these will do is they'll put numbers in like categories, like, you know, for example, truncate B3, everything is just a multiple of 8, which can produce very interesting effects, like effects that I can't even explain how they happen, but it just is pretty interesting. So these are all the modifiers, and these all work on const store. Now small const is a little bit different. This does not work off of that for a specific reason. Small const is basically a kind of a caveman's way, and I can probably improve the methodology of a lot of these functions. But small const, it basically looks for any constant that's less than 50, and it will randomize a number between 1 and 50 to replace it. And that's why I didn't really want to, I could put it here, but I didn't for whatever reason. It'll just throw a number between 1 and 50 back out to it. Now, const 0128 swap is an interesting one, because what this will do is, if you have, say, you load 128 into the accumulator instead of 0, in a lot of cases it's going to confuse the two. So for example, you load 128 into the accumulator and it, like, the game determines that this is a signed number that can be positive or negative. 128 is another way of saying 0, basically. It is 0 in terms of a signed byte. And so what it'll do is it will confuse. It's basically -0. It confuses the processor, basically, where you could be counting up when the processor wants to be counting down in that situation. It's a little bit hard to explain, but what this will do is this will swap those two values in order, hopefully, ideally, to confuse the processor and create some kind of upside downish effects in certain processes, etc. Compare branch basically means like in any programming, and this even includes in the assemblies we're working with here, you'll have stuff that says, like, if, say, Mario's lives is less than 10, then you perform this function, or you go here, and then you branch off there. They're called branches in assembly, which is just a fancy way of saying, if X is less than Y, then do this, or else do this other thing. And what this will do is this will corrupt the compare value, and so you can have a lot of cool unintended effects. Anything goes, kind of self-explanatory. It just means look for a byte to randomize and then randomize that. This is often good as a supplement. It's a wild card. It'll crash a lot of games, but there's a lot of things, there's a lot of effects that you're not going to get unless you just do pure random, because the more stringent you make your search, let me make sure all my stuff's working here. Yeah, the more stringent you make your search, the fewer impacts, the fewer potential impacts you'll have. And you'll see this with a lot of games. You'll see, like, if you use real-time Corruptor, for example, it produces awesome effects, but a lot of the effects get repeated. And it's the same thing with these two. And then you have these three JSRs here. JSR skip, basically what JSR is it's called jump to subroutine. And what that does is it'll say, here is the location of a certain set of instructions that I want to run. Go here, do all this, and then when you're done, return back to me, and then continue where we left off after I asked you to do this routine. That's basically what that means in assembly terms. And what this will do is this will skip over one of those, and so it won't run that routine, and it will go on to the next routine, and you can get some pretty cool effects doing that too. JSR equals RTS slash RTL. What this will do, RTS and RTL are basically the same thing. The difference is that RTL is like, it'll return to a 16-bit block of code instead of an 8 block of code. So JSR, the regular, will just take a normal 8-bit value. So that's basically just a fancy way of saying, like, these are the routines that are near what we're running. And then these other routines, the long routines, these are stuff that's far away in the program code of the game. And so what this will do is, instead of jumping to a subroutine, it'll return to a previous routine. And so not only is it going to skip, it's not going to do that subroutine, but it's going to return to the previous one. So now all of a sudden you're pretty much skipping all the routines that's going to happen after that. And then JSL equals PLA times 2. This is basically it's skipping a routine and it's canceling the previous routine. So it's basically, it's canceling the previous routine, and it's not going to return to that, but it's going to return to the next one. This one's a little more complicated, but it's interesting and it's something to try. But it basically says, we're not going to run the routine we ran previous to this one, which is kind of cool. These two, process flag invert, process flag neutral, basically on the processor there's certain what they call process flags. For example, you have a 0 flag. What the 0 flag is on the processor is, if the previous instruction you ran either wrote 0 or read 0 off of something. So for example, if Mario's lives is 0, and you say load this address, and this address contains 0, the address being the address for Mario's lives, then that will flag 0. And basically what this will do is this will say anything that tries to clear that flag gets inverted to setting that flag. So for example, if you have something checking if the number of lives Mario had loaded is 0, like if that's checked and that's not set, then the instruction will set that, and then therefore the processor could think Mario's lives is 0, which that's not, like, it's a good analogy for the process. That doesn't actually happen with the Super Nintendo specifically, but it just gives you kind of an idea of what the process flags do. And so it basically, like, anything that gets set, instead it will unset it. Anything that gets unset, it will set. Process flag neutral works the same way. What it'll do is, like, say you have something that says set the 0 flag that we were talking about, instead of unsetting the 0 flag, it'll just say keep the flag what it was. Like don't unset it, but also don't ignore the set function. Ignore the set instruction. Here's ink deck neutral, ink deck invert. Kind of, it's a little bit easier to explain. So what an inc or an increment instruction is basically it'll say increase this by 1. So you can increase the accumulator by 1, which again is just temporary storage on the processor to store in other addresses. So for example, when you gain a life, you will have an instruction that says increment address for Mario's lives. So it'll increase his lives by 1. And that'll be stored in a byte of data. And then dec or decrement kind of works the same way. And the way neutral works is instead of incrementing, so you collect that extra life, and it says increment Mario's lives, it'll just do nothing. So otherwise, no extra lives for Mario in that situation. Invert will turn increments into decrements and decrements into increments. So you collect an extra life. Not only does Mario not get that extra life, but he loses a life. He won't die, but his life counter will go down by 1. And who knows, maybe the death animation will play. I'm not sure how that would work, but basically that's how it would work. Is it'll do the opposite of what the instruction initially said. Corrupt DP reads, corrupt DP writes. A little bit more complicated. DP stands for direct page, and what the direct page is, it's just a small storage on the Super Nintendo of a set of up to 256 values. I think it might be a little bit less than that. I think it only goes to EF unless you have it set a certain way, but that's another technical story. So, but roughly, you're talking about 240 bytes, maybe, of data in the direct page. And what this will do is basically the direct page, what's stored on there, you have two types of things. You have links to different subroutines, such as, for example, routines of how Mario's jump animation works, or what happens when you get an extra life. And then you have actual stored values, such as Mario's life counter, or a frame counter, or any number of different things. And what this will do, corrupting the reads will say, if the value is read from, that is, you're not altering the value that is stored in this address, such as Mario's lives. You're not altering that, but you're just reading it. This will corrupt what is read. So, for example, if you corrupt DP reads, say the corruption chooses Mario's lives, something that reads from Mario's lives to corrupt, what this will do instead is it'll say, okay, we're not going to read Mario's lives anymore. We're going to read King Koopa's X position, initial X position when you get to the final boss, or something crazy like that. Or it'll say, like, Mario's jump animation. Instead, we're going to read what happens when Mario's head hits a question block. Something like that. And this will also corrupt math, like if you're adding some address to the accumulator, because you're not actually altering that address, this will corrupt that too. Corrupting DP writes means if you are writing to an address, for, going back to our example, Mario's lives, If you're writing something to that address, like you're writing the accumulator, or you're incrementing it, or you're performing some kind of operation on it, then that will corrupt what that number is. So it's basically the same thing, except for this will work with write. So for example, incrementing Mario's lives, as we said before, will, instead of incrementing Mario's lives, it will choose a different address to increment. So for example, if it goes to something that alters Mario's lives, say you like hit a one up mushroom, instead of doing that, it may say, okay, this now becomes Mario's X coordinate. So the mushroom may appear to do nothing, but it'll increment Mario's X coordinate by 1. So, you'll get your 1 pixel increase in his X coordinate, or whatever it would be. X is equal to Y, Y is equal to X. There's basically what they call 2 index registers on the Super Nintendo, and even on the regular Nintendo, the NES. And basically, these are used for indexing addresses mostly. So you got something called a loop. I'm not going to go too much into detail with it, but what it'll do is it will load something, set something to this address coordinate plus Y, increment Y, and then it will compare Y, or compare something, and then I'll go back and do the same thing again. So what this will do is this will say, like, all the Y's are equal to X's, and all the X's are equal to Y. So if an instruction modifies the X coordinate a certain way, this instead will say you're going to modify the Y coordinate in this exact same way. It probably doesn't help too much explaining that, because it's like, this is basically assemblies we're talking about, very, very abstract stuff. But just know, like, it works with stuff like loops, like, for example, like loading stuff to the graphics. That takes quite a few iterations of a loop. But I'm not going to go too much into that, because that's going to confuse the hell. Okay, STZ equals STA. This is a purely Super Nintendo instruction. STZ is just, it's called store 0, and what this will do is this will store the value 0 in a certain memory address. And all this will do is it'll say, instead of storing 0, you're just storing what the accumulator is. So otherwise, we're not gonna let these lazy programmers get by with just storing 0 in 2 bytes. We're gonna force them to store the accumulator in that. Oh boy. Okay, so now that we've seen this, let's go through some stuff. So what game did we load? We loaded Zelda. Zelda, we're actually gonna try a couple new ones. We're gonna try the process flags. The reason I like these is that their effects accumulate over time, often in games. Like, you play, for example, Super Mario World, or Super Mario Kart, it won't crash your game immediately, because these don't always have an immediate impact, because what this will do is it'll prevent what's called the carry flag from setting your clearing, or it'll set the carry flag when it's not meant to be set, which basically is a fancy way of saying you're either going to add 1 to this value, or you're not going to add 1 to it. Fancy way of saying that. Okay, so we're going to go through this, because I got to show you what this little monster is here. So we're going to go ahead and corrupt this. Um, so here's that. And I want to show you a couple cool tricks that you could use for this. So here's Zelda. We've done the process flags. And as you can see, let me get my controller. As you can see, we have a little bit of corruption here already. The Triforce will not move, but fortunately, we can go here, and as you can see, this is a little bit screwed up. Okay, so just to kind of show you what stuff looks like. Now, as you can see, the features of this are the Triforce music. Well, there's this. As you can see, we have quite a few problems here. We can't seem to do anything because there's a house in the way, and I don't have a sword yet because I'm working with the VT randomizer. And somehow I did this, and here's a cave. I wonder where this goes. I haven't ever... It goes nowhere. Well, somehow I'm staying alive. This is one of the more interesting ones. This is, and I think... Oh, I'm not stuck yet. We are still surviving, folks. Okay, so let's go back over here. Let's see if we can last a little bit longer here. Doesn't look like we can do a lot from here. But we're gonna try, because this is a pretty interesting one. This is what you can get, and you won't get this with... You won't... I mean, you'll get some pretty cool stuff with real-time Corruptor, but the thing that's good about this Corruptor, and the reason I'm just gonna publish this is because in a lot of ways, it's not superior to RTC, and I have a lot of respect for those developers, but you will get stuff that you're not going to get from that Corruptor. Because this is a fixed alteration, it doesn't alterate over time. And I think we're going to go ahead and end this for now. So let me go ahead and pause the simulation here, because there's stuff I gotta show you here. That was kind of fun, though, I gotta say. As you can see, there's these values up here, and this is the byte editor. And see, as you can see, a lot of these values are similar, and that's because this is just purely dealing with process flag alterations. And there's only actually several process flag alterations. Like there's the carry flag, overflow flag, interrupt flag, which I don't use for various reasons, because we're not interested in creating something that's going to crash the game 100% of the time, or 95% of the time. And so you got all these, right? Now you could go in here and edit these individually. So for example, you can go, I can put 22 here, and then you click edit. Now this is important, you got to click edit, otherwise it's not going to go through, the change will not go through. And as you can see, my 22 is right here. And then, of course, you can edit these individually if you know what you're doing, or you think you know which byte you can use. And kind of a cool thing too that will be added in the future 100%, I am going to add, this will be in what's called hexadecimal. Hexadecimal just means you have numbers 1 through 10, right? That's what's called the decimal system. The hexadecimal system works from 1 to 15, or 1 to 16. Yeah, 1 to 15 basically. The symbols are 0 to 15. And what that is you have 1, 2, 3, 4, 5, 6, 7, 8, 9, but instead of 10 as in 1, 0, you have A, B, C, D, E, F. And that represents 10 through 15. And then 16 is represented as 1, 0. And see, the importance of hexadecimal is, like, you see how 234 here. Like that would be like, for example, it may be EC or something. It'll be listed as, and all these will be listed as a 2-digit instead of a 3-digit. And like if you look up, for example, like guides to corrupting your ROMs manually, as in going in and editing the individual code, you're mostly going to see it in hexadecimal. But that's to come. But anyhow, what else can you do with this? Well, you can edit. Now another thing you can do is you can go 500 equals 500, and then you create new. And actually, no, I can't do that. So yeah, there's an example of an error. So it has to be between 0 and 255, the right-hand operand, because if you make it any higher than 255, then it's not a byte, it's something else. So we'll go 500 is equal to 200. And there's other bounds too that you'll get. And as you can see, there's the new value right here. 500 is equal to 200. So there's that and that. And now there's this scramble button. And what this scramble button will do, and this is where you can kind of combine a lot of these. So for example, these that I was telling you earlier, that you could not use this drop list on, like for example, small const 128, your branching, your JSRs, your process, all these things that you can't use that on. Now all of a sudden, you can. So all these inverts and stuff, instead of going through and editing these individually, you push scramble here, and now you see, look at the variety. Like now you have all kinds of different values. So, for example, and then you click use, and what this will do is this will recorrupt based on the same address as you corrupted before. So this is going to corrupt the same bytes, it's just giving them different values. Now, as you can see, that Triforce looked a little bit different, but you could see it got corrupted the same way. Like, if you need to go back in the video and see how the Triforce was moving before, it was moving along all 3 of its axes, and that time it was moving along too. Just a little observation. As you can see, a lot of these corruptions kind of look the same, but the difference is that the files haven't loaded, and in fact I cannot continue because and then you can scramble this again, and we'll actually kind of go through a few of these too, just to make sure you understand what these really do. So like we'll recorrupt these same bytes, because this actually is a really good corruption to test. So that was pure random. Pure random, as you can see, the numbers are everywhere. You got some very lows, very highs, some in the middle, and it's all evenly distributed, as you can see there. So for example, you go to random signed. Now, random signed, as we've went over, will retain the sign of the value. So that's a basic. So what that means in terms of this byte editor is anything 128 and above will retain that. So it will add 128 to whatever's produced. So let's see what that means. So first of all, you got 238, 165, 164, 2. So the only one that should be less than 128 when I recorrupt this should be this 116. So let's go ahead and scramble. And that is exactly what we have. Like, as you can see, these first 3 are above 128. This is below, and this is above. And that's what the random signed will do. And then you can... Now just be sure, do not push this corrupt button, because if you press this corrupt button, you are going to lose your corrupted bytes. It's going to create a whole new thing based on what you have checked here. And conversely, everything you have checked here does not affect what happens when you click this use button. This use button only impacts what is in here. It will only go through all these addresses and put in these values. And we've even got our custom addresses here. Okay, so there's random signed. Now 0 to 50, what this will do, of course, is just give everything a value between 0 and 50. So we got that, and as you can see, everything is between 0 and 50. And then 0 and 5, we'll go through that same thing, like everything we'll go to that. And then negative 50 and 50. This may be a little bit confusing, but what this is going to be is if the number is negative, it will add 128 to it. And the reason that is because the number 128 sets, like we were talking about the binary before, right? 8 bits to 1 byte. Well, the 7th bit is what's called the sign bit, and that is basically a fancy way of saying 128 and then plus your number. So just think of that. Like negative is 128 and above, all the way through 255. And so all these, anything above 128 is negative. Anything below is positive. So you'll see some of these are between 0 and 50. And then you'll have between 128 and 178. And as you'll see, none of these values will go above 178. So you got here exactly 128. And so that's an important thing to get. And then negative 5 to 5. Along the same lines, it will be between 1 and 5 or 128 and 133. So there's that. Now, of course, you're dividing by 2. Let's randomize this again just so we're on the same page. So now here's another little cool trick you can use. It's not perfect. There are perfect tricks, but like you divide these by 2. Everything will be divided by 2. So you saw that was 28 before. Now it's 14. And then you multiply by 2. And then you get back to 28. Now that's a pretty reliable way of canceling out at least most or about half of your corruptions. So you go back to where you were. With those, which is interesting. And then, of course, divide by 4, multiply by 8. It's going to be the same thing, except for different stuff. Now, invert sign, this is something where you can swap back. So, for example, let's corrupt this, and we'll see what this means in real time. And this one's actually a little more tame, for whatever reason. Oh, did I click, Oh, well, there's one thing. Link is orange. That's... So this should... It's not corrupting a lot of anything, really. Somehow this got to be a tame corruption. So let's try again. Let's try something where we can get a good effect. Just so I can kind of show you guys how you can kind of play with this stuff a little bit. Now as you can see right here, of course we got this, and then but we got this clear. And we kind of got the Bloody Link's house. Let's see if we can... Well, there's a corruption. Cool remix, bro. Cool remix. Is this even... Yeah, this is throwing bushes further. Look at that. Well, it was. Okay, so let's see this. Now let's try and invert the sign. And let's see what we get. So let's click use. And this didn't seem to get corrupted too much. And as you can see, we got this back. And as you can see, this seems a lot more tame. And we have completely crashed the game. But no worries, because you can invert the sign again, like so, and you will get back to the corruption you had previously. And as you can see, we're back here with the bloody text again, and we're going to get the crappy music with the far away bushes. And as you can see, we're back to normal. And the same thing can work with the mirror. And so let's mirror this, and we'll just show you that it works. And let's see if we got Triforce. It seems tame. This is about the same as it was with the bloody text. And the signature right there is the sound. So of course, oh no, the game crashed. It's okay, because we get back to here. And again, mirroring just subtracts the byte from 255. So instead of having the number, you just have 255 minus the number. And we're going to be back to the crap music. And sometimes, now this won't always work, but sometimes you can do, for example, multiplying by 2 and then dividing by 2 again. Now this won't always work, because what this does is, because of the way multiplication works, it will overflow the 255 value, but it will set a value based on how much it went over. In other words, it's called ANDing a value. So you AND a value, for example, with 255, you're only going to get a value between 0 and 255 based on how much you overflowed the value. So we can multiply this by 2, and we can use it. And see, this won't be completely reversible again, but this is a way where you can at least try and alleviate the impact of corruptions. And as you can see, most of the time here, this is actually crashing, so we got really lucky. So instead of multiplying by 2, you divide by 2, and then you click use. And then we'll see what this does. I'm kind of interested to see what this creates. It's probably not going to be remarkable. We're probably going to crash again. And we almost didn't crash. But something loaded in the memory and we just had to crash. Okay. So, I just want to show real quick the, we're going to go ahead and load. We'll go ahead and load this, and we'll just give a few examples of truncation just to see what it looks like on the byte editor. And I can explain why it looks the way it looks on here. As you can see, we crashed, but we don't need to have a game here to explain what this is. So this is, as you can see, there's only going to be 0s and 128s here. And what that means is, like I said, this only retains the top byte. So it only returns byte 7. So for example, if your original number was 114, it doesn't matter what any of the other bytes are. If the higher byte, which is again 128, if that's not set, then it goes to 0. If it's over 128, then it's only going to retain that byte, so everything else goes to 0. Again, truncate just means everything after this point is 0. I don't care what it is. And I can even give you a mathematical example. So let's just say you have a number that is 1.9999. Like in mathematical terms, if you round it, it rounds to 2. If you truncate, it doesn't matter how close that number is to 2, it truncates down to exactly 1. And so this works off of the same concept, basically. You are turning everything after that point to 0. You're only retaining everything after. And so what does this look like for byte 6? Well, let's corrupt that, and we'll go to byte 6, and then we'll see if this produces anything good as a little bonus. And nothing wrong with the animation here. And we go back to the title screen when we push start. And we crash. But again, we don't need to really run the game in order to see what happens here. So now you have 4 sections here. So what this is doing is it's returning the first 2 bytes. So basically what this means in those terms is you either get 0, 64, 128, or 192. Like, you're only going to get those 4 values. So, if you remember nothing else about the truncating, or understand nothing else, understand this is going to give you 1 value. This is going to give you 4 values. This is going to give you 2 different values. This will be 4. This will be 8, 16, and 32 different values. So let's look at what this looks like with truncating B5. So let's go ahead and corrupt this, and we'll have a look and see if we created something cool or something that sucks and crashes right away. See, a lot of the higher bytes, like, you can get by with the higher bytes, but I generally recommend doing the lower ones, 3 or 4 or 5, but there's gonna be unique effects to using every one of them. But using the lower ones won't crash your game as much, because it's basically sectioning off something to more of a similar value. So you're not gonna get like absurd changes. Okay, so as you can see, this kind of produced, as you can see, a lot more minor of a change. So let's look at what this looks like here. As you can see, a lot more values, but it goes by increments of 32 this time instead of 64. So whereas before you had 64, 128, and then 192, this one you have 32, 64, 96, 128, 160, and then 192, and then you even get up to 224 here, which is the final section. And then these other ones will create kind of the same thing, but I'll go ahead and run them for y'all because, at least you'll know what values you think you should be getting. And we get the Master Sword at the title screen. Let's see if this produces anything. I'd love to see the Master Sword animation play out on the title screen. But sadly, nope, we just picked it just ran the music. But as you can see, this is going by intervals of 16 now. So you got 16, 32, 48, 64, etc. 160, 240. So this will go by increments of 16. And then this will go by increments of 8. And that's as low as I wanted to go. I could truncate it B2 and B1, and I might even add those along the line. But I've actually got better solutions for those. I'm going to have, like, I'm actually going to start adding some individual byte operations on here. And so those will kind of replace that, like increments, decrements, by certain fixed numbers. And the purpose behind that would be you're not deviating a great amount from the values that were being edited before. Okay, so let's go ahead and do B3, and then we're going to go ahead and wrap this up for this version of the Corruptor. And we get no Nintendo thing, and now we get no sound. And I get no movement, and I have no control. So that's that for this, but let's look at what this looks like in the byte editor, because again, more important, this works off of, every one of these will be multiples of 8. So you'll see, like, the maximum right now is 248, whereas before it was 240. So there's all that, and this produced quite a few zeros. But yeah, so this is the first version of my Corruptor that I'm releasing to the public. I'm not expecting anything off of this. I just mostly, if you can help with anything, just give some feedback on what I can do to improve this. I can't really make this like a real-time Corruptor, because what I'd have to do is I'd have to connect this to BizHawk, and I don't want to do that here, because see, what this will do is when you select a file here, it's just going to load whatever you default loading this to, and that even includes non-game files. So if you're loading some other file format, it's going to load that too. Now granted, none of these are really going to be useful for that, at least not useful in obvious ways. Because if you're loading like a Word document or something, the assembly for that's going to work very differently than on a processor from 30 years ago or whatever, which is what this is. Like the Super Nintendo, it works off of the old Motorola technology. Not even like Intel or any of that, just Motorola, and they have different instructions, different registers, and the registers work differently and all that. I mean, assembly works the same, but the way things are mapped is very different. So anyhow, I'm going to go ahead and upload this, and this will be available for download immediately. You just check the description. Thank you guys for watching this tutorial, and I will be out with more game corruptions very, very soon, probably today. Thanks for listening.